Boron has a rich chemistry with hydrogen, forming combination with unusual stoichiometries and structures. Boron hydrides are also known as boranes, and its generic stoichiometric is BnHm or BnHm. The study of their bonding has required the expansion of molecular orbital theory in order to explain their unusual stoichiometries. Borane shows a tremendous extensive reactivity which is quite different from that observed in organometallic and organic chemistry. One of the most unique aspects is that hydrogen atoms often act as bridges between neighboring boron atoms. They are seen in a simple diborane molecule. In this structure, it is shown that the borons of diborane is bridged by two hydrogens. Each boron presents 4 bonds corresponding to a sp3 hybridization, forming a pseudo-tetrahedron structure around each boron atom. 2 of the 4 half-filled hybridized orbitals of boron will be involved in the bonding of one s orbital of the 2 terminal hydrogen atoms. The third single half-filled hybridized orbital overlaps at the same time with the empty half-filled hybridized orbital of the neighboring boron atom and the 1s orbital of the bridging hydrogen atom. This arrangement will result in a single orbital that encompasses all the 3 atoms, and this bond is called as banana bond. It results in only 2 electrons to connect the 3 atoms. Another arrangement forms the other BH3 bridge. This situation generates as a result every covalent bond, commonly known as 3-center 2-electron bond. As a result, the bonding electron distribution of diborane is shown in the following molecular orbital diagram. This is as simple as 2 boron atom is involved, but in a more complex borons, higher number of boron atoms arranged in the form of well-defined polyhedron. These polyhedrons are commonly known as deltahedrons because they contain equilateral triangular faces of boron atoms, for example tetrahedron and octahedron. There are 3 common classes of borons such as closoclasters, nidoclasters, and arachnoclasters. Closoclasters are the boron's atoms form a closed deltahedron cage, and the generic formula is BnHn2-. While nidoclasters are open cages derived from closed deltahedrons with 1 boron missing, and the generic formula is BnHn+4 or BnHn+3-. For example, B5H9. Whereas arachnoclasters are also open cages derived from closed deltahedrons by removing 2 boron atoms. So the generic formula is BnHn+6 or BnHn+5-. So the example is B4H10. Synthesis of boron hydride. Boron hydride can be prepared from the reaction of metal hydride with diborane or boron trihalide. Diborane can be obtained from sodium borohydride and boron trifluoride, from lithium aluminum hydride and boron trichloride, or with reduction of boron trihalide with hydrogen. Equation shows formation of diborane, and so in the same way B5H11 can be obtained from B4H9-. Higher borane can be formed by controlled pyrolysis of diborane, which lead to a mixture of higher borane. These higher boranes react in the same way like diborane.
Heteroboranes. Heteroboranes are classes of boranes. At least one boron atom is replaced by another element. For example, azaborane, that its boron been replaced by nitrogen, and the second one is carborane, that it will been replaced by carbon. Example of heteroborane is carborane. Carborane is any member of class of organometallic compounds containing carbon, boron, and hydrogen. The general formula of carboranes is represented by C2BN HN+2, which n is an integer. Carborane with n ranging from 3 to 10 have been characterized. Like many of the related boranes, these clusters are polyhedral and similarly classified as closo, nido, and arachno. So this is of covering. Coverings are generally prepared by reaction of acetylene derivative with boron hydrides. So this is reaction carborane. First, nidoborane will react with diethyl sulfate, produce arachnocarborane, then react with ethylene, will produce closocarborane. As is the case with boranes, the nido and arachnocarboranes are less thermally stable and reactive to air and chemical reagents than corresponding closocarboranes, most of which are stable to 400 degrees Celsius, although they may rearrange to more stable isomeric forms.
Weight rule is a correlation between number of electrons in a specific way. The formula and shape of molecule was established by Kenneth Wade in 1970. Used to predict the structure of polyhedral borohydride. Boron hydride structure includes simple polyhedral closo compound and then progressively more open nido and arachino structure. Building block from which the deltahedron is constructed is assumed to be one BH group that contributes 2 electrons. Available to the skeleton, which is the B atom, provides 3 electrons and the H atom provides 1, but of these 4 are used for the BH bond. Counting electrons. Residual electron is known as the 2 electrons assigned to each BH unit. For the definition of skeletal electron, the rest of the electron in the cluster. Skeletal electrons are calculated according to the following rules. First, calculate the total number of valence electrons present in the compound, counting 3 for each boron, 1 for each hydrogen, and the corresponding charge.
Properties of borane. Borane is an inorganic compound with chemical formula BH3. The structure of borane is a trigonal planar. It is a colorless gas that cannot be concentrated in pure form. It is both the simplest member of borane and the prototype of the monorenes. And lastly, it is soluble in water and ammonia. BH3 will react with sodium BH4 and will form diboron gas, and the equation of reaction was stated as below. Diboron gas is a highly toxic, flammable, and also easily explosive. Properties of heteroborane. Boron trihalides are useful Lewis acid. This is because they are important atrophies for the formation of boron element bonding. Boron oxygen B2O3, for example, boric acid, it is very with boric acid in aqueous solution. For boron with nitrogen, which is Bn, it is isoelectric, but it also analogous of graphite and diamond.
Application of borane and heteroborane. Uses of diborane. Diborane may be used as a rocket fuel for supersonic aeroplanes, a starting material for preparing higher borane metal boron hydride such as LiBH4 and ABH4, etc., a catalyst in polymerization reaction, a reducing agent in organic reaction. Other applications. Borosilicate glass, a type of glass which a very low coefficient of expansion make it more resistant to thermal shock than conventional soda glass. It is widely used in chemical laboratories and kitchens. Sodium peroxoborate is used in laundry industry as color-safe bleaching alternative and as ingredients of dishwashing powder and tablets. This application is based on its power as an oxidizing agent as a result of two peroxide groups linking the boron atom. Boron nitride has many applications. The main use as thermal insulator, giving its low thermal expansion and it resistant to thermal shocks. It is used in cosmetics such as nail polish, lipstick, due to its sheen, softness, and non-toxicity.